Okay, guys, you see what I'm live, and I think I am. Hope you guys are doing well. Let me share this here. Paper reading plus improving the fuzzy dedupe logic. And let me share the paper with people there. The paper name is Building Machine Translation Systems for the Next 1,000 Languages. Let me just share the abstract link. Okay. With that out of the way, I want to start by skimming the paper, and then we can continue improving the fuzzy deduplication. Actually, a person from the Luther AI server just sent me, so Haley just sent me this code for file deduplication. So that's going to be something we're going to check out. Okay, actually, this person has the same issue. I'm currently having an issue with my Ubuntu. Just a second. So there seems to be some fix. Reinstalling operating system fixes for 3 to 6 months. Okay. Let's go back to paper reading. I want to focus only on the data. I think I've read this paper before, but like it's a good idea to just check out the data sections, data cleaning in particular. So let's kind of skim the abstract and then go to the data section. In this paper, we share findings from our effort to build practical MT systems capable of translating across over 1,000 languages. They describe results in 3 research domains: building clean web-mined datasets. Okay, by leveraging semi-supervised pre-training for language identification, and developing data-driven filtering techniques. And then second, developing practical MT models for underserved languages by leveraging massively multilingual models trained with supervised parallel data. And 3, studying the limitations of evaluation metrics. Using this approach, we add 24 new languages to Google Translate, the product's largest increase in language coverage to date. We hope that our work provides useful insights to practitioners working towards building empty systems for currently understudied languages. Okay. Building the data, building the models, evaluation, conclusions, and appendix section. Let me see what this is. Table 23. Let's go back to the beginning. I'm not sure I've read this paper. Might be good to put this one on the reading list. Maybe under literature, and then reading list. Let me see what interesting sections we can check out, because I don't want to go through the whole thing. Let's see the main findings. Starting with the initial seed dataset of monolingual sentences spanning over 1,500 languages, we demonstrate that it is possible to build relatively clean, web-mined, monolingual text datasets for over 1,000 languages. We highlight the importance of incorporating expressive semi-supervised LangID models, document-level consistency signals, and several word-based and custom filtering techniques to identify and filter web text in long-tail languages. Okay. They then train on that model. They highlight the importance of model capacity when training highly multilingual translation models, and the positive effect on zero resource quality when increasing the number of languages in the model. We also describe the significant quality improvements achievable by incorporating a large-scale back translation and self-training, and share our findings towards developing practical inference-friendly models for long-tail languages. Okay. Let's go back to the beginning again. Importance of native speakers. That's why we have the language champion doc, among other things. Since the advent of statistical and then neural machine translation large data sets, let me just skim this quickly. It's important to build a relationship with native speakers. How to help them understanding the data. Understanding errors in reference translations. Specialized filters. transliteration and political sensitivity around script. Understanding crowd worker annotations. Classifying utility for community. Okay, commenting on dialects. Many languages have a wide variety of dialects, sometimes hardly unintelligible. Okay. This is definitely going to be a useful paper to read. It came out, I think, maybe even before the NLLB paper, which came, I think, in June 2022. Interesting. Special font that provides glyphs for these ASCII code points. Nice. CHRF score, where the source uses different versions of common Unicode points. The top line of each block represents the correct code point, whereas the lower lines are other ways of representing the same letter. In many cases, there is very little difference in performance, but the African languages are affected by non-standard characters. Okay. There was some interesting insight here. I didn't know this. So literally using ASCII code points and then special font to render that visually. I was wondering what's non-Unicode, because yeah, it makes sense now. There are many different ways to write certain letters, especially those where a Unicode standard was introduced after a population was already active online. Okay, too idiosyncratic for us to now read that or learn anything. You just skim through most of this just to get some feeling for what's going on. But mostly we care about data cleaning. Okay, let me check whether anybody is asking any questions. Will you save the recording of the translation? I'm not sure what you mean by save the recording of the translation. Even after having been distilled on a mix of clean and noisy, we observed that some of these languages still had lower performance on inputs that lacked terminal punctuations. To study this, we compared performance on devaluation sets with and without terminal punctuation. The gain is small but consistent. And for out of the into English, 100% of language pairs benefit. Okay. Okay, this is definitely going to be super relevant once we start expanding the scope. Okay, let's go to data cleaning section. Let's just go to the beginning and see. Okay, so from page 6 to 12. Okay, there is a ton of interesting sections here. Let's skim through this one. Well, there are over 1 million sentences per language present in our corpus for the highest resource languages, 200 languages. The median number is only 43,000. Okay. Comparing the performance of 1.5B and 6B models. These experiments were conducted on an earlier version of the dataset spanning 112 supervised and 94 zero-resource languages. While small amounts of parallel resources weren't difficult to obtain for many of these languages, preliminary experiments did not result in any quality improvements. Okay, experimental setup. All our models based on the standard transformer architecture, 32 layers, 1.5 and 6p. Okay, so 3 types of tokens, 2 task, 2 translation, 2 mass for the mass task. We find this to be critical for zero resource performance, especially when model sizes are scaled up. In the absence of this token, our models learn to infer the task from the source languages instead of relying on the 2xx token, resulting in copying sentences when provided zero resource language sentences with a... Okay. We first compare the effect of model capacity. Results shown in table 3. Let's see the textual description. Significant effect when increasing to 6p. Okay. Continual learning, extending models from 200 to 1000. Align the SPN tokens shared across the 2 vocabs and assign them the same IDs. We compared the performance of our 200 language model against a 1000 language empty model. Okay, let's skim through the rest here. Distillation. Okay, let's go back to the data part, data cleaning and filtering. That's somewhere here. Hello, Ayman. Okay, it is difficult to uncover large, clean, and highly multilineal corpora from the web. Okay, just trying to skim this to extract information, so I don't want to read everything out loud. That would make me slow down. Omit languages from the lang ID with poor quality training data. Cluster languages. Document consistency filtering. Percent threshold word list filtering. Okay, the semi-supervised models use the mass objective, but they're much slower to run. Training and evaluation data identical to this work here. It trained on the aggregation of proprietary and publicly available corpora with an average of 800k, almost a million tokens per language. Paring down the set of languages. Following this analysis, we removed 116 languages from the model, primarily based on poor quality training data. Among these, most were regional dialects in Europe. Okay, false negative rate clustering. The cluster based on this FNR. Since some of the clusters were still excessively large, we resplit the largest one by hand, such that no cluster had more than 20 languages. Document consistency filtering. So for every sentence they apply lang ID prediction. This is one of the simplest and by far most effective filtering steps. They disregarded any sentence whose sentence level lang ID cluster prediction did not match the document level cluster prediction. Okay. investigate the effectiveness of document consistency filtering, we looked at the document consistency score for a given sentence in a doc. The document consistency score is simply the percent of sentences in that document sharing the same lang ID prediction as that sentence. Therefore, if the document consistency score is over 50, it will never be filtered out with document consistency filtering. Figure 1 shows that deciles for document consistency scores across all languages for a sample web crawl with the initial CLD3 model. Okay, let's see how we should interpret this chart. The large mass of sentences with a low document consistency score indicates that there are many single random sentences in larger documents, including non-linguistic content, whose language is mispredicted. Of the 0.55% with document consistency scores over 90%, over half had a score of 100%. Huh, what does that even mean? So for a given sentence in a document, the document consistency score is simply the percent of sentences in that document sharing the same lang ID prediction as that sentence. So that means we had like 0.3% of the documents only had 100% consistency across sentences in that document. Okay, this is not relevant to us because we already know what's the language in every single file, so we can just apply the LID detector to filter out incorrect languages. But now setting the threshold and all of that is kind of dark magic. A sentence was discarded if it had less than 20% in language words, where the word lists were the most frequent 800 words from the lang ID training data. Okay, so they have most frequent words for each language, and then if a sentence had less than 20% of those high frequency words, then they drop it. EFIIF filtering. Okay, this is less relevant to us. Examples in language D mispredicted as L. True examples in language L. And then just the numbers of those. False discovery rate. Okay, this is, I guess, more relevant if you're doing data collection and mining. Okay, let's just see. I didn't find anything super practical and directly usable in this paper. Let me see if there is any questions. Okay. So even after the filtering steps described in the previous sections, a variety of languages still had data quality issues. One issue that was not easily filtered out by approaches like TF-IF was templated content, which is technically in the right language, but is not useful for training data. To a lesser extent, we also saw issues like the unlucky Engram effect. Okay. Why is this called and speak? Does anybody know? When you have like spaces between the letters. Why do people call that and speak? Huh. Okay. Nah, I didn't find anything super useful in this paper, honestly. Let's see how we are progressing with the run here. Okay, that's some heavy filtering going on there. Excuse me. Okay. Let's skim through the pile code for the duplication. Generate the min hashes. One process per logical core. Verify the min hashes. Dedupe. Setting the threshold. Okay. Archiver, what is this? Whoops. Reader. Open the file. Use the TQDM. Total unit as progress. And then mmap. And then they go through the mmap and they decode into UTF-8. And then we yield the line. I think this is the main file. Python dedupe. Once they have the min hashes, I think this is the main file. Dedupes the pile using an LSH build with the provided min hashes. Duplicates are output as pickle dumps. Min hash from data sketch. That's the same thing we're using. Yield min hashes. query for found offset in results. If found offset is different than the offset, then what? Duplicates append, offset, and results. Only remove the self. Okay, this is the logic that we need to figure out. There is the lsh remove command. Okay. Generate the min hashes. What's this file statistics? File start offsets. What exactly does this mean? Is this like number of lines? Or like bytes or what? Load the checkpoint offset. Yield file. Slice to document. Extract the engrams. Update the set. So they use number of permutations 10. Okay, they did mention that in the paper, and I'm recognizing a lot of the code here as well. We've done similar things ourselves. Okay. This script generates a lean mint hash for each file document, which is saved along with the document offset into a series of files. Lean mint hash. What's a lean mint hash? With a smaller memory footprint and faster deserialization, but with its internal state frozen. Okay, some optimization detail. Provides helper functions for working with the file duplicates. It's runnable for displaying duplicate statistics and inspecting the duplicates. When inspecting, we build an index mapping. This is the interesting one. Load the data. And yield the offset and found offset. Okay. One would have to run this step by step to understand exactly what's going on. Okay. Hey Dave, it's about the Open NLLB project. If you haven't seen it already, check out the, let me open up my server here and check out the Open NLLB channel here and also the pin posts. You'll see a bit more details there about everything relevant to the project. Okay, we kind of skim through this. There is a lot of dumping of pickle files and picking them up and parallelization, and because of all of that, it's kind of confusing how this exactly works. I was trying to just see the logic behind how they create these connected components, but I failed to do that, honestly. Insert, let me see where is insert mentioned. So this is the only place where it's mentioned. That's where we insert, and then query. I think this is also the only place where they do the query. So query, we get the results for found offset. So what results gives us back is, let me quickly open up my code here. Query result. Okay. And what we get there is whatever we used here with insert. So that's the logic. So when inserting, what are they doing exactly? What are they inserting? Okay, they're inserting the offset. And the min hash. Working with min hashes. So grab the min hashes directory, find all of the files that have this format, then sort them according to what? Search and then convert into the integer the group 1. Okay, sort the min hash files according to this number in here. And then for file in those files, we load them to get the data, and then we go and yield. But who produced this in the first place? Yeah, I see some format that looks like what we are looking for. So this function seems to be dumping these min hashes. So process batch. Okay, so they first so in the main file, in the main function. So again, first generate the min hashes. Which does what? We specify process count. Parse the arguments. Create a working directory. That's where we're gonna dump the min hashes. So again, min hashes are just these signatures. So given a sentence, we can shingle it and use that to create its min hash. So in the pile implementation here, what they do is they basically dump those as pickles first. So let's go to main. So it's expecting to find the pile directory. And then they grab the statistics and the document count. And then they create a checkpoint pickle, checkpoint temporary, old, and lock. And then if the lock exists, program crashed during transaction fixing files. If the checkpoint temporary exists, then if the old one exists, then we rename the old one to the new one and then remove the temporary one. What does this exactly do? Okay, we'll see how this transaction lock is created. But if the temporary file exists and we try and use that as a checkpoint file, otherwise we just remove the transaction log. If the checkpoint file exists, then we open it up in the read binary mode and we load it to get the offset. Otherwise we start from 0. TQDM multi-process pool. Is this their custom class or what? From TQDM multi-process. What the heck is that? So is that just your regular multi-process primitive plus the TQDM, I guess? That's Elu3i's package. Okay, so they create the pool and then start running yield pile. That probably just grabs a document from pile. Again, let me see where is pool used. In the process batch. But before that, they call the yield pile. Working with pile, yield pile. Returns a generator for pile documents starting from checkpoint offset if supplied, or the beginning otherwise. Fair enough. Gets the pile files. So grabs all the file in this JSON ZST, whatever that format is, sorts them and brings them back. So once we have the files, if there is the offset, then we start okay, these are some details specific to pile, I guess. So file start offsets, we can iterate through those. And if the start offset is bigger, Once the start offset is bigger than the checkpoint offset, we break and then that leaves us with start file being equal to the previous offset index. And then go through the files. Pull the reader, go through the documents, and yield the global offset and the document. What's the set standard? What's this one? What's set standard package? Z standard compression library. Open source. Real-time compression developed by Facebook. Aims to provide high compression ratios, fast performance, and reasonable compression-decompression speeds. The primary features and benefits that makes Z standard special, especially when used in Python or other languages, include high compression ratio, speed, very fast, tunable compression, rich dictionary-based compression, streaming, safety and reliability, and wide adoption. I've never seen it before. Okay. So what the reader does is, let's go back here. Again, working with pile, yield the pile, calls the reader, and then passes on file to the read function of reader. It opens the file in binary mode. creates the compressor, the buffered reader. Calls the stream reader on the file handle. And yields the data. Okay. Is that like text? Okay. So that's the yield file. It brings back the document and the global offset. Okay. Back to the generate min hashes. So it gives us the offset and the document. If the offset is smaller than the checkpoint, then we just progress, update, and continue. We skip everything, and then if the offset equals checkpoint offset, then we reset and update. Okay. Batch append, and only when the batch size is of particular size do we process the batch. So process the batch of documents, and then at the end, once we are done with that, if there is still some data in the batch, we again call process batch. Okay, so the whole function happened, the whole brain is in the process batch. So we pass in the pool, the progress, which is the progress bar, I guess. See what it is exactly. Progress. Where is this progress thingy defined? That's the TQDM context manager. Okay, and then process batch. So full progress batch, working directory, and backup directory. Okay. Process batch. Go through the offset and documents. Task is going to be generate min hash with the document, and then append. Progress, full map, progress. We pass in the tasks and these two functions, on error and on none. This is probably going to be lazy execution, and only now that we start iterating through the generator do we start executing the tasks. So instead of offset document, we now store offset min hash of the document. And then we dump all of the offsets and min hashes to the file. And then transaction lock. Okay, they just do some simple locking mechanism using an actual file on the file system. That's interesting. And the whole logic happens in the generate min hash actually. So given a document, they first slice it up. So if the length is bigger than megabyte, then the slice size is a megabyte. How many slices? And then slice it up. So here are the slices, and then we go through the slices. We extract the 5 grams from the slice and use that to update the 5 grams set. So extract engrams. Calls the engrams from NLTK. Where it tokenize the data. And then we join them. Huh, interesting. So what's the difference between what smart thing does this do compared to what we have implemented before? Which is just this. Get the shingle set, we just do simple iteration and extract the 5 grams. And then we create a set out of those. And then we grab those 5 grams, unique 5 grams, and we encode them into UTF-8, and then we use that to update the min hash. Hi, Andre. So what's so special with this? Let's try and install it. What does this do? To download the datasets, tokenizers and other resources are necessary for using certain functionalities, but aren't indeed included with the initial installation. refers to the punked tokenizer models. Pre-trained, unsupervised machine learning tokenizer. Okay. So grab the slice again. We have a slice. Each slice is smaller than a megabyte. And then we pass in that slice. I guess the slice, is that gonna be just a string? It's hard when there are no notations. That's the thing with Python, like process batch. Let me see quickly. Just backtrack and figure out what's the document. Is it just a string? The easiest thing is to just run this. I'm not sure why am I analyzing this inside of a browser in the first place, but yeah. So batch offset document comes from the yield pile, which comes from working with the pile. So yield pile. Document is whatever the read gives us. Whatever the read gives us, that's the document. And that gives us a piece of text. So hopefully this is just a string. Okay, so having seen that, all we need to pass in here is just a sentence, like let's see what we get here. Okay. So first of all, word tokenize data. It's gonna give us what exactly? Will it just split this? Okay, this is a test, more data, more data. Why? What's so smart about word tokenize? Return a tokenized copy of text using NLTK's recommended word tokenizer. English. Okay. Okay, where did I lose that file? And then once we have that, then we bring in the Engram. So we tokenize we first tokenize the sentence or the document in general. Then we pass in 5 and we get the engrams. Huh. Interesting. Let's just convert that into a list. This is a test. Aha. So this one gives us engrams, but not on the level of characters, which is what we've previously been doing, but instead on actual tokens. Interesting. So then I think I might have depleted the... Let's just rerun this again. Yes. And then it basically just joins the grams. Yeah. Okay, makes sense. I understand what it's doing now. Let's go back here. Go back to generate min caches. Okay, and then we get the engrams, and then we update this one with those engrams. And we keep on doing that for all the slices for the document. And then once we have that set of engrams, of shingles, how they call them, we go through those and we update the min hash with encoded versions of those engrams, 5 grams in this particular case. And once that's done, they'll return back the lean min hash. Okay, interesting. I guess the reason they're working on tokenized engrams as opposed to what I'm doing is that they are dealing with huge documents, and in that case you don't want to do something like I'm doing, right? Because I'm doing character level engrams and they're doing word level engrams. Okay, I don't think either one is incorrect. So generate min cache. That's going to be the task again. And tasks are passed on to the pool. And that one yields us the min hashes. Okay. So once we have the min hashes, we have the min hash and the offset. And we save that. And then we dump that as a pickle. Okay, so for each batch of documents, we will end up having a certain number of offsets and min hashes. Okay, this makes sense. And that's it. That's the whole logic here. So now that we have this, now we go through this logic here. So again, so far the only difference has been that they are shingling using the NLTK's word tokenizer. Okay. Let me just see one more thing. So again, they take this document, all the slices, extract the engrams from the slice, which is like a megabyte in size, up to megabyte, and then update. Equivalent for me is to grab a set of engrams from a sentence. So I would get engrams on a character level and update the set. And then I use that to update the min hash. Let me quickly go through the code. So again, here is a sentence that's equivalent to their document. And we get the single set. As you can see here, we create a set of character level engrams, and then shingle by shingle, element by element, we encode it and put it in there. Okay. Let's see what this final file does again. Close the main. Min hashes directory is the input, and output will have the duplicates. And then the threshold that they use is 0.5. So they use 0.5 and they have number of permutations set to 10. Let me just ask them in the server. Let me just ask Haley. Okay. Back to the pile, the duplication logic. So calling the main, creating the output duplicates directory, the done file if it exists. Okay, otherwise we pick up the statistics from the duplicates directory. We create the LSH pickle, load or create the LSH, and they pass in the directory. Okay, let's see how this one is defined. If it exists already, then they just load the LSH and then retrieve it back. Otherwise, if this is being run for the first time, we create the min hash LSH with the threshold of 0.5 and number of permutations 10, and then they go like document count, pass in the min hashes directory and then yield min hashes, and then they keep on inserting those. So offset and min hash, and offset and min hash. And then they dump LSH as a pickle. Okay. Working with min hashes, let me just quickly check that one. Okay, get the files. And then data, and then one after one, they keep on yielding. Okay. Each one of those contains the min hash for a particular document. That's it. So again, LSH is not dumped. That was the load phase. So again, that was the load or create LSH. Here it is. Do we actually retrieve back the LSH? Yes, we do. The LSH object plus we dump it. And then what they do is start yielding the min hashes again. Now it's the query time, and then they query. Okay, so this is the whole logic. So they get the results, and for the offsets in the results, okay, this is going to be the fun part. Let's make a quick break, and then we can continue analyzing this one, just to see whether they have the implementation that I need. Then I can reuse it potentially. Okay, guys, quick break, as I said. Just need to stretch a bit. Let's open up the to-dos here. 5-minute stretching break, or even shorter. maybe like 4 minutes. Okay, guys, catch you in a couple of minutes. And we are continuing on with file fuzzy analysis. Okay. Okay, guys, I'm back. Okay. Maybe a bit longer break than I thought. But now let's see how the logic here works. So we query, and then we go through the results, which contain the offsets of the respective documents. If the found offset is different than the offset, which is what? Which is what exactly? Aha. If it's different than the offset of this particular document, in that case, we add that to the duplicates. We just append. We say, hey, here's the offset, and here are the results. And then duplicate count plus 1. And then we remove. Aha, we only remove the self. What? Wait. Aha. So they go through the results, which might be like 5, 10 candidates or whatnot. And if it's different than the offset, in that case, wait, this doesn't make sense. Aha. They immediately break, then it makes sense, okay. So the first time that we find a document that's different than the current document, we append to the duplicates the current document together with the results, which is a candidate pool, and we remove this one, the self. Okay. And then if the length okay. Yeah, this makes sense. Okay, I think we can actually easily implement this on our side as well. So if the length of duplicates equals the save frequency, in that case we save the duplicate batch to the duplicates directory and then ensure there is enough disk space, which basically just checks, I think I've seen it above there, disk usage. Okay. If length of duplicates at the end, if it's different than 0, we save again and save the stats. That's it. Okay, this is actually much simpler than I thought it will be. Got it. We can easily implement this on our side, guys. So what we do is query and then for if the index is different than the current I, then we just say LSH then we just say self LSH remove. Was that how they've done it? Just remove LSH removed and then the offset. LSH remove and then the offset. That's it. This is literally it. Okay. We might be able to integrate this into the pipeline without having to have a separate process. If you recall what I've done before here with the filtering pipeline. So again, we grab the current index of this line. We don't need this anymore. We don't need this. We don't need a set here. We just, okay, we update the line because we extracted the index. We create a min hash for this particular line. We query, we get the results, we go through the results, and if any of the indices is different than the current one, we remove and we break. So just remove it. Actually, sorry, we remove the current one. So again, we remove the self. Remove the current line. That's literally everything that they do. Of course, there is the counter here, and they additionally are storing all of these because are they later they're later inspecting the duplicates. What do they do when they inspect it? Let me just share the results here with the folks. Inspect the duplicates. Let's see what this does. Get the stats by passing in the duplicates directory. So this one grabs the file if it exists, then we'll load the stats. What exactly do we store there? Wait. They save the duplicates stats. Threshold and count. That's all. And now they load it. get the file statistics, percentage remaining. So original minus the duplicates over the original. That's how many percentage it remains. And then if inspect, then we call the inspect duplicates and we pass in the duplicates directory. Verify file documents. Was this ever stored as a part of this logic here? I doubt it. Otherwise, it doesn't exist. Yield the duplicates. And then index documents of offset is none. And then they go through the found offsets and they say index documents of found offset is none as well. And then increase the count. Okay. So then they go through the yield file again, document and offset. If the offset is inside of the index, in that case, we say indexed documents of the offset equals document. And at the end, they just dump, and then they will do what? Yield the duplicates again. Aha. Okay. This is actually fairly simple logic. Let's go back to the filter file. Let me just think for a second. Yeah, we can definitely do this as a part of the whole process above without having to have this separate logic here, which is super cool. Okay, guys, so that means we grab this. Okay, the problem is again, the issue here again is that we have to pass in all of the lines. To form the filter. I'm still thinking what's the best thing to do here. Let me see whether anybody is asking any questions. All good. There is a trade-off here. Obviously, it's much neater to integrate fuzzy deduplication inside of the existing pipeline. That's on the one hand side. On the other hand side, that would mean we would have to pass in all of the original corpus sentences to the constructor. Whereas here, we just have to pass in the filtered ones, which is much smaller number. So what's the best way to do here? Let me see what they've done in the pile. How do they manage the creation of the LSH again? LSH is created here, and then one after one they yield and yield and yield. And yielding does what? Loads a single file. Okay, yields a single min hash, one at a time. So they avoid having the peak memory. That's what I would love to do as well. We should be able to do that. So line at a line, keep on adding. Okay. Thinking what's the best thing to do here. This is our LSH. We go, but the thing is we've loaded already everything inside of the source lines and target lines. So that means we have a very high peak memory, which is limiting. Ideally we would do what? Ideally we would... Why not just pass the paths? Wait, just a second. Why not just... Huh. So here we do deduplication across a single direction for all of the corpora inside of that direction. That's what we do. Well, let's do the same thing here. Datasets. Let's just pass the datasets, guys. If we pass the datasets inside of the constructor, then we avoid having the peak memory. I think this will work. We avoid having the peak memory, and then yeah. So the solution is like this. We grab this, we put it as the last filter after the exact duplication. We pass in this one. So it looks like this. And then we pass in the, instead of source and target lines, we just pass in the dataset. And datasets is dictionary of string to dataset. Okay. So now we go to configs, go to fuzzy, remove these two, instead just pass in this one, call it datasets, and make it of this type, and make it equal to none. And then we need to just specify what this dataset is. We need to import this inside of the configs. Will this be fine if we do this? I think it will. Okay. So now we have datasets. And it's set to none. Looking good there. Go to filter. Okay, we've got ourselves a filter. And that means that we can now remove all of this. And this, all of this can be removed. And we will need to add this hacky line. And we need to add this as well. So go to the filter, to the dedupe. And here just add something like this. Counts. Exactly. Go back to filter. Remove this. Remove this, this. We don't need any of this. We just need this. Put that inside of the filter line. So we'll have to do a quick hack here. So we'll have to do something like line source, but under certain condition only. And that condition is, wait, we don't need this again. We can immediately write this instead of appending. Okay. That's it. With a couple more modifications. So only if the filter class name is this, do we do something like this. Okay. Looking much better. Let's see what the changes are. We don't need this. So we have this additional logic, normalized line, all of that is good. This as well, this as well, this as well. Nice. And the last step is to go to the filter. Sorry, dedupe, where are you? Okay, here it is. Again, we extract the line. We modify the source so we can remove what we encoded inside the line number. We just remove that from the line source. We create the min hash. We normalize for deduplication. We query, and then we go through the results. If the index is different than I, if there exists other candidates other than I, we can safely remove I. In which case we return back none. Otherwise, we return back the line. And that's it. Awesome. This should really work. Same as here. If we need to filter it out, we return none. And otherwise we return a line at the end. Awesome. This was such a simple implementation at the end. So query, go through the results. If it exists, if other candidates exist, then we can safely remove current line and increase the total after fuzzy. Aha, this is actually a mistake. We don't need to, it's not the total after fuzzy that we need to change. We actually don't need that one at all. We don't need it. We just need the pair fuzzy dedupe. That's the last change I think we have to make. Exactly. We just basically note inside of the counter that one of the lines was filtered out because of the fuzzy duplication. Okay. That's it, guys. We're just left with tuning the filtering hyperparameters and kicking off the filtering job. And that's going to be hopefully ready by during the night, and then tomorrow we can start working on the prepare data stage. Let's see where we stand with the previous preliminary one. If I put a breakpoint somewhere here and check out the results here. Why is this so slow? Okay, it looks like the other ones are done already. Temp test. Is there any total? Okay, here we have a total already. Only 1 million. $15 million before. What about Croatian? Huh. Something is weird with these numbers. Something is super weird with these numbers. The total before should be much bigger. So total happens only after we are done with the run. Why would we have only wait? Oh. Okay. Makes sense. This is because this is train primary. We are yet to go through the train mind. So we are still processing only the train primary. Okay, makes sense. So let's see the numbers again. For Serbian Cyrillic, we are left with 2 million lines, and we started with roughly 4, so like around 50% of the data was filtered out. As for Bosnian, results are even worse. We started like with 15 million and ended up with a single million. That's a huge ratio. And Croatian is still being processed. Why are we so slow to... Why are we not doing this in parallel? Or we probably are... like directions should be handled in parallel. As you can see here, batch size, we should grab all directions in parallel and then call filter group with group name train primary with all directions, and then there we should again do the batch, go over directions and just submit. Huh, interesting. Okay. Um, let me just see whether somebody's pinging me regarding the talk. Again, let's quickly just skim through the changes. Configs and filter. Configs. I think all of this is good. If there are any issues, I'm gonna patch it subsequently. But I think all of this was good. This as well. All that is good. Init, I don't have to change that. I think. Let me just see quickly. Yes. And then base, dedupe LID toxicity, base, okay, LID, we just have the HBS. I didn't change that one. Toxicity, I didn't change it. Dedupe, I did change it, and we know it's good now. Let me just see whether there is anything redundant here. I think this is also good. What else? Okay, these two are good. This is good as well. Symbols and TMP. What's the TMP? I'm not sure. Okay, this was just my testing of the pile implementation. And symbols is again nothing that I've touched there. Awesome. Let's add all of those. So add the configs. Add the filter. Add the init. Add the base. Add the dedupe. Add the LID. Toxicity as well. I should probably add the git ignore so I can just do git add all, but for now I'm just doing this manually. Okay. That's it. All of the other ones are just YAML or TXT files or prepared data, which we don't care about. Okay, so with that we have we added symbols, fuzzy, toxicity. Okay, for this I have to paste some token. So with this, guys, we're wrapping up this session. I'm just gonna push this to the repo, and we are now waiting for the filtering pipeline to finish. After the preliminary run is over, we can kick off the new run with the fuzzy deduplication and see the results there. Okay, guys, I'm wrapping up the stream as I said. See you in the next one. I guess in a couple of hours I have a talk. If you want to join in 8 p.m., so that's in 30 minutes, we'll be having Christoph Schumann of Lion Glory. So let me show you. If you never heard of him, they're the folks behind many interesting projects like datasets and models. So he's going to be giving a talk about previous and future projects. So do check it out. With that, I am logging out. Cheers, guys. Bye-bye.